This lecture will explain the basic truth tables for each of our connectives. We'll start with the truth table for conjunctions. Conjunctions are pretty straightforward. A conjunction is true only when both conjuncts are true. So that's pretty much what you would expect. Disjunctions are also pretty simple. Once you remember that for us, disjunction will always be taken as inclusive unless explicitly specified otherwise by the use of the phrase, but not both. So if we have an inclusive disjunction, then a disjunction is true whenever one of its disjuncts are true, or when both of them are true. Importantly, it is false only when both disjuncts are false. So that's what it means for a disjunction to be inclusive, and that's how our disjunctions will work. Okay, negations are also very, very simple. The truth value of a negated statement is always the opposite of the truth value of the unnegated statement. So if P is true, then not P is false, and if P is false, then not P is true. Okay, conditionals are a little weird for people. So the way we interpret conditionals in sentential logic is we say that they are false only when the antecedent is true and the consequent is false. So that's that second row on the truth table. Now, it doesn't weird people out generally that when the antecedent is true and the consequent is true, the conditional is true. But it does tend to weird people out that when the antecedent is false, look at the third and fourth row. When the antecedent is false, the conditional is true, regardless of the truth value of the consequent. And the best way to think about this is to think of it as sort of an untested hypothesis. So if I have the hypothesis, if I eat a piece of chalk, then I'll die. Well, if I eat the chalk and I die, so that's like the first row of the truth table, then my statement was true. Eating chalk kills me. However, if I say, if I eat this chalk, then I'll die, and suppose I don't eat the chalk, but I die anyway. So now we're looking at like the third row of the truth table. So suppose I get hit by a bus. At that point, my hypothesis, if I eat chalk, then I'll die, is an untested hypothesis. But it's still possible that it's true, that eating chalk kills me. And so we take it as true until we know otherwise. Likewise, if I don't eat the chalk and I don't die, we still haven't tested the hypothesis, so we still take it as true. But however, if I eat the chalk and I die, so we're looking at the second row of the truth table, or I don't die, excuse me. If I eat the chalk and I don't die, then we know that the statement, if I eat chalk, then I'll die, is a false statement. So this isn't exactly what's going on with all conditionals, obviously, but it's just sort of a good way to remember the truth tables for the conditionals and to see it as something sort of plausible. Okay, and then finally, biconditionals. So remember, biconditionals are if and only if statements. For example, you may go to the movies if and only if you clean up your room. So we can expand this statement. You may go to the movies if you clean up your room, and you may go to the movies only if you clean up your room. That's really what if and only if is a shorthand for. So we would symbolize this as, so the first, these conjuncts are actually sort of in reverse order to how they occur in the statement. And there's a reason for that. But so C, arrow G is you may go to the movies. No, sorry, they are in the right order. So the C, arrow G is you may go to the movies if you clean up your room. And then the G, arrow C is you may go to the movies only if you clean up your room. But logicians are lazy. We could write out both of these conditionals and join them by and. And that could be just the way we symbolize biconditionals. But we're lazy. So we're going to say, you may go to the movies if and only if you clean your room. And this IFF is a shorthand, lazy way that logicians like to write if and only if. So sometimes you may see that. And we're going to collapse those two conditionals and write G double arrow C. Now let's look at the truth table for the biconditional. So compare the truth tables for Q arrow P and P arrow Q and P if and only if Q. And you'll see that they're the same, because the Q arrow P and P arrow Q is really what underlies the P if and only if Q, as we discussed on the previous slide. It's really these two conditionals joined by an and is what underlies it. And that explains why the truth table works out the way it does. If you kind of draw the parse trees for Q arrow P and P arrow Q and work out all the truth values, this is what you'll get. And so it turns out that biconditionals are true only if the truth values for both sides of the biconditional match, and they're false otherwise. So when P is true and Q is true, P double arrow Q is true. And when P is false and Q is false, P double arrow Q is true also. But if P is true and Q is false, or if P is false and Q is true, then P if and only if Q is false. And that actually makes some kind of sense. The thing, again, that might kind of weird people out is that when they're both false, it's true. But if you look at the truth tables sort of in detail, you'll see why this is.